All right. Well, thank you very much to the organizers indeed for doing this, because it's so important, so timely. I'm so excited to be here and talk about some of the work that we've been doing at the University of Bristol. I have dual affiliation, but everything I will talk is with my university affiliation. And it's about on-sensor computer vision with pixel processor arrays, something that we've been doing since quite a long time now, at least since 2012, I started talking with Piotr Dudek, who had developed these pixel processor arrays as part of his PhD more than 20 years ago. And since then, we have been working with a team of students and colleagues to try to see how computation on sensor for visual systems can actually improve. And I know that everyone here is pretty much familiar with what that standard visual pipeline looks like. But just as a reminder, we often believe that in computer vision, a camera is just there to capture images. And of course, cameras were developed for that reason, for capturing weddings or events for humans, but not necessarily as sensors for artificial systems that need to act in the real world. And so the traditional pipeline will indeed flood the limited bandwidth that you have with a bunch of images and information that then needs to be ferried around a bunch of order processors that may involve standard CPUs, GPUs. Eventually, you might send information towards motor controllers, and eventually you get an action, right? So this is like the sad picture of how computer vision for action works in the traditional way. Even with event sensors, we have been hearing a lot of about that. But one reality in many of the event-based systems that try to improve on this aspect of the bandwidth reduction, you still have to go and reconstruct a lot of the information on the back end. And this might not always be the most efficient way of doing things. So with an approach of pixel processor arrays, the idea is that at the time of image capture, you're able to do computation. So you're able to already start to make decisions, classifications, matching, even reconstructions, limited ones, but potentially a bunch of other tasks, so that after that, after you are capturing light, you're immediately able to translate that into action. So you're reducing bandwidth. So you might be sending things like, what is the direction estimation? What is the location of what I'm tracking? Or what is the identity of that thing? But nothing else. So you're not trying to send only information that is not useful for the rest of the pipeline. You're sending information that is very high level. And eventually, directly, you might be able to send signals, even motor control signals, as we have done in some of the experiments, to go directly from capturing light to action. And I think that's a very interesting paradigm that can be facilitated by being able to do computation on sensor. And why would you want to do that? Well, the same reasons why many of the speakers here have referred to. So low latency, limited bandwidth utilization, and reduced system complexity, limited energy consumption. So all the things that really matter when you want to do things in the real world. And we might wonder, well, is there a neuromorphic connection with doing on-sensor computation? And it turns out that there have been some very interesting work from the 1950s from Ledvin, Maturana, and McCulloch, some very important figures in the neurophysiology world, where they discovered that this is meant to be a frog that at the time my 7-year-old drew for me. In the eyes of the frog, there are things that they described as bug detectors. They were laughed at first, because how can the eye be doing anything but just sending information from the outside world to the brain? But it actually turns out that inside the retina for the frog, there are things that trigger not only when they discover something that has the size and color of a bug, but also behaves like a bug, right? Not just spatial discrimination, there is behavioral discrimination. Very basic, very rudimentary, but they're able to do that, right? So this is in the retina. And why will the frog want to do that in the most efficient way? Well, because you want to catch the prey, right? So that immediate reaction, limited computation, a lot of energy savings happens, and there are correlations with in the animal world exists, and so this comes to architectures that try to do that level of computation, potentially much more than what the frog is able to do. And this is a SCAMP architecture by my colleague Piotr Dudek. I mentioned he did this as part of his PhD more than 20 years ago. And the SCAMP is a pixel processor array, where what you have here is for every pixel, every single pixel has a CPU, a very basic CPU, but it has memory, it has registers, it has flags, it has an ALU, and is connected with the neighbors. So you're able to do parallel computation at the time you're capturing images, right? And this, of course, opens all these possibilities similar to what we've been arguing that the frog should be able to do. The ALU that you have here and the type of things that you can do are very basic, but it's still sophisticated enough for you to do some of the things that I will talk about later. But just in simple terms, if you want to understand how this works, imagine that you have, for every pixel, you have multiple registers, and you can imagine that these registers, A to, let's say, Z here, you have an image copy, where you have a memory where you can actually store the images that you're capturing, and you can then do what you will do in a normal processor. You can subtract, you can add, you can shift, and by doing that, you can do pretty much a lot of the low-level computations that you could expect to do. But you can do that very quickly, pretty much as instantly as you're capturing light. You can compare images. You can differentiate between images, lots of things. And we have indeed done a bunch of things that allow us to do things like estimating the yaw, pitch, and roll tracking. We have been able to do perspective correction on the image plane. So we have put this in drones, and the drone is flying at an angle. How can we actually correct the image for simplifying the matching? So everything on the image plane. HDR, at the moment you're capturing light, so you can use, it also has analog registers, so we can actually do computation of HDR as we are capturing images. So we don't have to do anything else outside of the sensor. And these type of basic algorithms that you can imagine, as long as you think carefully about how you're going to design them, allow you to do a lot of things. So, for example, we did back in 2017, so several years ago, in ICCV actually, there was a visual odometry paper with PPAs running at 1,000 kilohertz. And it's actually 1,000 hertz. This is wrong. And the way in which we did this is that we essentially just capture an image, distort that image slightly, like move to the left, move to the right, up and down, slightly bit of zoom in, and then we compare those distortions that we generate with the incoming image, right? So you capture the image, you distort it a little bit, you compare it with the next image, you can estimate which one corresponds better, and that gives you an idea of how much you have moved. If it matches with the one that is zoomed in, it means that you have moved away. Or it matches with the one on the left, you have moved to the right, and so on. So you can actually compare very, very fast all these distortions so that you can actually create a visual odometry system that is running at 1,000 hertz on the image plane, and you can estimate how you're moving. So this is an example of that. I think I have a visualization of this later. So the camera is moving, doing these computations, all on the image plane, and then you estimate. This is a trajectory estimation on how that sensor is moving, just based on these very basic computations. One thing that is very important when you have this type of architecture is to rethink the type of algorithms that you are putting there. So now you have a parallel architecture, you can do computation on the image plane. You really need to rethink about the type of algorithms that you are developing. Otherwise, you won't be benefiting in full. We have also done other basic things like put this on a drone, and the drone is estimating its attitude towards these gates all on the image plane, where you have these gates and the PPA is actually figuring out based on the shape of the object there, what is its attitude, and then it actually sends the command controls for you to go through these gates. We have even been able to put very basic convolutional neural networks on this, because this is a massive parallel array, and convolutions, well, they are just shifts, right? And if we do the right logic, we are able to do some CNNs on the image plane. And again, this is another ICCV paper a few years ago where we were able to do very basic CNNs on the image plane, classifying digits, and also doing a little bit of tracking and detection. So in this case, it's kind of detecting an object and tracking it out and so on. So yeah, this will be an illustration of that, how you would do this type of CNN on a pixel processor array, all happening on the image plane. You have an input image, you can duplicate that image, then you do convolutions, you apply all your ReLU operations and max pooling, and eventually you are able to classify what this object is. And it's possible to reach speeds up to 17,000 hertz on a CNN on this type of plane. I'm not here to say that this is the way to go, because we first need to figure out if you need 17,000 hertz to do this type of task. That's a different question. But hopefully gives you the idea that you can be much more efficient and much more energy aware, and handle that energy and bandwidth much better if you can do this on the image plane. And there's a bunch of papers that we have done with that. Maybe one of the most interesting ones that to me was very nice to be able to demonstrate that we could do is actual mapping and localization on the image plane. So very simple mapping is image-based mapping and localization, but the idea here was that we put something like a particle filter that essentially was just moving around, capturing images. So what you see here is the capture of images, and the sensor was able to accept or reject images that were similar to what it has seen before. So it just doesn't capture all images that are useless. So it actually does a little bit of logic in terms of what thing is mapping, but it's capturing images. And as it captures images, it also estimates how much it has moved. And then when you try to localize, then essentially we have implemented some very basic particle filter on the image plane to match the incoming image to an existing image and apply a particle filter that estimates that motion as you are moving. And we have done that with existing data sets and also our own data sets. This was an ICRA 2021 paper that demonstrated you are able to actually do things as sophisticated as localization and mapping at the time of image capture. All right, so if you're interested on an overview of what we did so far, there is a Science Robotics paper 2022, the sensor level computer vision with pixel processor arrays. We go into all the details for all the different things that we tried by then. So this was kind of the culmination of the existing research projects with between University of Bristol, my team, where we do the computer vision algorithms, and University of Manchester, Piotr Dudek's team, that they do the PPAs. But of course, we were not satisfied with what we did there, so we actually now got a new project. And this new project that we started just last year, it's a 4-year project where we're very excited to ask this question. I already showed to you a bunch of things you can do on the image plane, but I think a much more interesting question is what should happen where, right? Where should we do that computation? I mean, I demonstrated fancy things like mapping and localization on the image plane. Yeah, if you need to do it, maybe that's the right thing, but maybe it doesn't have to happen there. Maybe that or parts of that needs to happen in different parts of that computational continuum. And this project is now involving another university. So now is Andrew Davison and Paul Kelly from Imperial College. And they're also looking at compilers and computer vision algorithms. So together, we're really working towards trying to answer this question of where, what should happen where. And what does this mean? So just to reemphasize these aspects of the traditional pipeline. So far you have something like a camera, you have something like a PC, and normally you will expect that you will have that intelligence happening on the back end. But as we bring this type of new sensor processor in play, then you can still have some intelligence happening on the PC, but we can also try to bring some intelligence, so distributing the intelligence across these 2 or maybe more components, which brings us to what I will call a visual computation continuum, where you might have on one end, you can have on-sensor computation. On the other end, you might have the back end. But you might also have near sensor and near back end modules that allow you to compute so that you can distribute that intelligence in different parts. So remember about the frog, and even in the human visual system, ganglia in the optic nerve actually appear to be doing some computation as well. So it's not that everything happens on the brain or on the eye. There can be a continuum of intelligence that can be distributed. And on one end, let's say on sensor, you might have things like events. On the other end, on the back end, you might have things like long-term memory, a global 3D map that requires a lot of memory and resources to be maintained. So the back end sounds like the right place for you to do that. But then you have a bunch of other visual competences that you might be interested in distributing along this continuum. So you can have feature description, feature detection. Maybe depth estimation can happen much nearer to the sensor. It doesn't really have to happen in the back end. Relative 6D pulse estimation. Even object identity could be happening near sensor or maybe on the sensor. There are things that you can split, like relocalization tasks, right? So maybe you have a big map and you just send to the PPA a small portion of the map to do the matching there, right? So the PPA could be doing that. You're estimating where you are, and you don't have to send the full map, or you don't have to send the full image. So the sensor can actually be helping you to do that already gated localization. And then you can imagine a bunch of other things. Even the CNNs that I mentioned to you, you could have things that happen near sensor. Part of them can happen near sensor, part of them could happen near the back end. And a big question mark for your preferred algorithm for you to put in there, right? So where should computation happen? So I think that is one big important question that I'm genuinely very interested in trying to answer. And this takes me to this second part where I will just briefly talk about a paper we have here in ICCV. It's a poster paper, Thursday session, 12:30 to 4:30, where what we're doing here is trying to do feature matching and detection on the image plane. So this is work with my student Hongyi Zhang and now collaborators from Manchester. Laurie now is back in Bristol. He is amazing collaborator. And what we're trying to do here is imagine that you can detect features and describe features, even match features without having to leave that sensor processor. So no images leave that camera, no images have to be ferried around, only the results of the matching are sent. Why would you want to do that? Well, we already spoke about energy efficiency and latency and all that. Privacy could be another interesting thing, right? That you're doing all this matching of what is happening or who is there. And only when you have a validated result that is privacy aware, maybe you're sending that information in an encrypted way out of the device, right? I will not be claiming that our system currently is able to demonstrate any privacy whatsoever, but that will be an example motivation on why you will want to do that, right? And emphasizing again why it's so important to try to bring that partition of computation through that and along that visual continuum is that when you want to do things in the real world, and now I will briefly put on my industrial hat. I have been in projects where the width of the cable or the bandwidth coming out of the camera kills the project, right? Because the thermals and just the physics of things don't make it work, right? But if you're able to do a lot of computation and save energy at the moment you're capturing light, then, for example, the bandwidth and the energy consumption will be much reduced, if not entirely eliminated as a concern, and that makes things happen in the real world. So it's so important to really start thinking about how things work in the real world when you try to push the boundaries for visual computation. And well, this is
local plane visual.
This is just self-illustrations on how this method that we developed works. So on the right-hand side, you see the template image that you're now matching with something that that is moving around, changing perspective, and so on. And all of this is happening on that on sensor on the image plane. And of course, if you can do this, then you can start thinking about things like more sophisticated localization and mapping. This is working out in the wild. The way in which this works is that we use basic feature detection to initiate points where we are interested to describe, and then we describe those regions using an old but still good by one of my colleagues and friends, Vincent Lepetit and his team, the brief descriptor. The brief descriptor, if you are not familiar with, essentially is a collection of pairs of sample points, and you essentially just compare, is this pixel brighter than the other one, right? And you do that multiple times, and your descriptor is essentially that comparison of these pairs of pixels, and that's how you can describe that region. So very simple. If you do that on the PPA, you will have to do that by shifting the images, but this is super fast, and you can then bring these pixels into the right locations for you to do the matching, and oh, sorry. And then you are able to perform this at hundreds of frames per second. Actually, this algorithm, which has not been optimized whatsoever for speed so far, is about 200 plus frames per second. And the description is one part of what this paper does, but then we also go into how do you actually store these descriptors, which are the largest in pixel descriptors we're aware of, so 128 128 bits descriptors that you also store on the pixel processor array, and when they are stored in there, you can also match with the incoming descriptors that you are capturing on the current image. The way you do the matching is that you essentially replicate the descriptor you want to match against, and essentially you just do things like XOR, and you find which pixels match the most, and then you do some summation, and you figure out which one is the one. There's a sandcastle algorithm in there that we use in order to figure out which one of those rows is the one that matches the closest. So we have tested these on a bunch of different data sets that essentially test for different perspective distortions, and also the Oxford robot car data set that actually compares this on the wild for images that you have a lot of occlusion changes and so on. And we're able to match very, very closely algorithms that are 94% of closeness to algorithms that are off the sensor. So from the point of view of this work, our system is able to generate and store these significantly longer descriptors, all on sensor, up to 128 bits. We're able to do the matching on the sensor, and importantly, apart from the good accuracy that we're able to achieve compared to off-sensor systems and the high frequency, we can reduce up to 100 times the bandwidth if we had to send the full images and do all this matching off-sensor. So these are significant savings. That brings me to some of the conclusions of the work so far. So vision for action does not need to be, and likely should not need to, follow conventional pipelines. So as we argued, cameras were not really designed for action, but to record images, and recording images may not actually be what computer vision needs to be for a lot of acting systems out there, right? The notion of splitting sensor from decision making, I think, is flawed. And thinking about this visual computation continuum is a much more interesting paradigm, in my opinion, because then it liberates us from just thinking computation can happen only one place, sensing can happen only in another place, but spreading that computation through that continuum, it's very important. It brings this important scientific question, which is what should happen where, and I think I don't yet have an answer for that, or how to even get to that. Some ideas, but no answers. And then the hope is that by the community exploring all these different avenues for where to do computation or how to do that computation is going to push the limits of what our current systems are able to do. With this, I finish. Thank you very much. And if we have time, happy to.
Any questions from the audience? Please.
It was really interesting talk. I like the one slide in the visual. It's more of a pessimistic question, so take it as you should. So imagine a situation where we get cameras where near sensor compute has high throughput bandwidth, they're able to transfer images from the camera onto near sensor compute more effectively. Is that going to be a more desirable solution than in-pixel compute? Because in-pixel compute comes with its host of challenges. You have to transform algorithms, you have to do a whole bunch of things, the ecosystem will inevitably lag mainstream computer vision. So will just developing near sensor compute be a better solution, or are there fundamental reasons for pixelized compute?
Thank you for the question. I think that's part of what even ourselves who are working on this type of systems are constantly debating about. I do believe that there is genuinely reasons why you want to do a computation as soon as you're capturing light. I do think that there are genuine reasons why you will want to do that. But I also believe that there is going to be a lot of scope for near sensor computation, where maybe a reduction of the information already happened, but not sufficient for you to just send and limit the bandwidth compared to a traditional pipeline. So I will not be a true scientist if I say this is the only way to do things, right? I do believe that us as a community exploring this continuum, where should happen where, will guide us better in terms of, is it near sensor, or what should be near sensor, what should be on sensor, and so on. And different systems may have different compromises that will dictate as well what is the right opportunity. But I just want to say that near sensor is as important as on sensor, in my opinion. So, thank you.
Any other question?
Yes.
Out of curiosity, how many watts does the scan?
Right. So another great question. The algorithm that I just showed you, without any optimization on the hardware or the USB used for communication, which consumes a lot of energy, is 1 watt. Okay, but we believe that there is significant opportunity for saving because nothing has been optimized.
And how available is the scan?
Is not available. Piotr, my colleague, is trying to set up a company. We are also wanting, by the way, I want to mention that we are aiming to organize a workshop at CVPR for on-sensor and near-sensor computer vision. And we might actually have the opportunity for the community to apply to get SCAMP devices so that more people can work with them. So, but right now it's not commercially available. It has just been between my colleague Piotr and some universities. I can put you in touch if you're interested, but it's difficult. These are research devices, right? So, but
presumably a amount of chips available.
Yes, not many. I mean, actually, I have only one, and I've been working with Piotr for 15 years. Yes.
The resolution.
The resolution 256 by 256, which is a lot. When I did my very first Visual Islam papers back in 2003, that was a resolution we're doing Visual Islam with. So you can do a lot of things with that. So.
Any other question? From the audience online? Yeah.
No?
From online?
Online?
Hi. Thank you for the talk.
Thanks, Federico.
I guess you might have already answered a little bit about this. But so, how far do you think these kind of cameras are from being commercially available? I mean, from being usable in a commercial environment?
So a lot depends on the availability. That, yes, we touch a little bit, right? So the more these devices become available, I have come across, I don't want to talk about them because it's nothing really certain yet, but I have come across perfect matching opportunities between this type of sensor and some devices that are out there, right? But the availability, improving the technology will be crucial for things to start being adopted. So everything really hinges on making this type of devices available. So I think that's a big block at the moment. But I don't see something fundamentally flawed from the point of view of why would you not be doing this if these devices were available. Maybe with the exception of the programming. How do you program these devices is not exactly intuitive, but again, that is a little bit of additional work as a team we have to work on to make that programming more available. So.
Thank you.
Oh, another question maybe? Do we have time?
Yeah, sure.
Sorry. Please.
Very explanation. I have one question that I approached this industrial. The first, I have the question that the fixer matrix, and it needed heavy conversion. So very heavy to our conception. So in that compound, in my camera system, so that has each piece is heavy conversion. Do you have it?
I think I understood your question, which is about the analog conversion from the photodiode. Yeah. Yes. Yeah. So the CPU is actually an analog CPU, so you're already making savings with that, right? So that's a very interesting architecture that Piotr. I'm not the one that designed the architecture. My colleague Piotr is the one, and I'm not the electronics engineer to answer the question. But my familiarity with the SCAMP tells me that that may not be a big issue, but is much better if Piotr and my colleagues from the engineering side answered that. But the fact that you're using analog CPUs already simplifies some of that energy consumption. So I don't know. Do we have time? Another question? Or?
Yeah, sure.
Okay.
Maybe it's understand correctly. What kind of sensor is CAMP connected to?
What kind of sensor?
Yeah, is it event sensor?
No, it's a photodiode. So.
Thanks.
Yeah. So we can get grayscale images. Yeah. So even color, we had the Bay array or filters. But, so. Yeah. Thank you very much.
Question. Thank you again.
Thank you.
It was